Welcome. In last few classes, starting from the fundamental subspaces, we observed that the fundamental subspaces are mutually orthogonal to each other, and from there what we took a case that the B vector does not lie in column space. So, B vector has a component in left null space also. As left null space and column space are mutually orthogonal to each other, we projected B vector into column space, and the remaining part we will say that this is in the left null space. In the using the projected part of the B vector into the column space, we form the normal equation and we solve the normal equation to get best estimate. The idea from this exercise we got is that a vector can be projected into a space and the left out part will be the orthogonal part to the projection. So, if we have one particular vector, we can project this vector into another space and get the projection, and subtract the projection from the main vector and get another component which is perpendicular to the projection. So, we can constitute mutually orthogonal components of a vector, or we can decompose a vector into mutually orthogonal components. And this idea now we will explore more, that we will have a set of vectors which are mutually independent, but not orthogonal to each other. And now we will start projecting one vector to other and subtracting the projection from it, and then that way we will create a set of mutually orthogonal vectors, or if essentially we will create a set of orthogonal basis vectors for any vector subspace. And this process will start from a set of mutually independent vectors and which are not necessarily orthogonal to each other, and end up with a set of mutually orthogonal basis vectors, and also these basis vectors, each of the basis vector will have a length unity, and this process is called a Gram-Schmidt orthogonalization process. We will look into Gram-Schmidt orthogonalization process, we will see what are the advantages and how this can be further applied for developing better matrix solvers. So, we will shift little bit from matrix solvers, we will see how to orthogonalize the vectors given any set of basis vectors, and then we will again come back to matrix solvers, how this can be used in order to solve Ax is equal to B, as well as in order to solve the normal equation A transpose Ax tilde is equal to A transpose B when Ax is equal to B does not have any solution. So, we go to the first slide. What is given here? Sorry, that we have a matrix equation, we consider it is in a column combination form, and this is in the vectors are in R2, it is real coordinate space of dimension 2. So, it is easy to visualize it. So, these two columns are 3 2 and 4 1, and they are combined to get a resultant vector which is minus 5 0. So, if we look into the column space, the basis vectors are 3 2 and 4 1, and these basis vectors are inclined to each other. They are linearly independent vector, but they are not, and any combination of these vectors can give me a vector in the column space. However, these vectors are not perpendicular to each other. So, this is some point, certain cases we make this mistake that bases are always perpendicular to each other, because we deal with bases like x y z or e theta e z e r, something like that in Cartesian or cylindrical coordinate. However, basis vectors can be inclined to each other also. We consider a matrix equation in R2, that means in real coordinate space R2 or in 2 dimension space, the vectors are member of the real coordinate space R2, and we consider the column combination form of this equation. So, this can be written as some constant multiplied with 3 2 plus some constant multiplied with 4 1 is equal to minus 5 0, and we have to find out what are these constant coefficients through solution of the matrix equation. So, if I look into the vector space or the column space here, the column space is constituted by the vectors 3 2 and 4 1. They are basis of the column space, because in R2 we need only 2 vectors which are linearly independent to form the basis. And this is interesting to observe that these basis vectors are not mutually orthogonal, they are inclined to each other. sometimes when we think of basis of any real coordinate space, we think of x y or x y z or r theta in, if we think of in polar coordinate, which are perpendicular basis vectors. That is very easy to use, very helpful to use perpendicular basis vectors in geometry, but and we will see why it is important in a moment. However, basis vectors may also be inclined to each other. In general, basis vectors are inclined to each other, they are not at 90-degree angle in between them, but our exercise will be to form orthogonal basis vectors, that is the next thing. So, however, in this particular case, when the basis vectors are inclined to each other of the column space, if I try to solve this equation geometrically, that means I will take the first column vector and multiply it with a coefficient and then add it with the second column vector, multiplying it with another coefficient and see what are the coefficients. So, geometrically this is not trivial. For 2D even we can think of solving it like this. We will extend this line and we will extend this line, we will keep on extending this line and then start drawing parallel of this, and then we will see, we will do multiple parallel of this, and then we will see that this parallel of this particular vector meets at this point, and this is minus 2 times into this particular column and 1 time into this particular column. So, minus 2 and 1 is the solution. For 2D it can be visualized, and it is difficult exercise if we think of doing it for even for a 3D case. You have to draw a line and several parallels, take parallels in the plane, it is not trivial. So, what we can say that when the equation has unique solution as the columns are basis of R2, however, it is not trivial to find the solutions using simple geometry. Using simple geometric construction, here for 2D we can find it, if it is 3D it is difficult to find. However, if we have an equation where the columns are not inclined to each other, the columns are perpendicular to each other. If we consider this equation system 3 0 and 0 1, these columns are mutually orthogonal. The solution can be very easily found out simply by project the B vector into one column, the columns are perpendicular to each other, project the B vector into one column. So, this is 6 0, x will be 6 by 3 is equal to 2, and the remaining part project it into another column, this will be 0 2. So, y is equal to 2 by 1 is equal to 1 in this case. So, solution becomes extremely straightforward. Just by projecting B vector on the columns, we can find out the solutions, and dividing it, getting the length of the projection, dividing it by the length of the column vector, we should be able to find out the solution. So, if we have a matrix where the columns are orthogonal to each other, solving the matrix equation also becomes very simple. It is only you have to take each column, project it, and we have seen how to project a column into a vector onto another vector. You have to project the B vector onto that column, find out the length, divide by the length of the column, it is the solution associated of the is the coefficient associated with this particular column, and go on. So, this is one advantage where we can, for which we should seek for mutually orthogonal columns. Now, if we look into equations with mutually orthogonal column, it is easy to solve equations in Rn if A has mutually orthogonal columns, and we have seen that. Projecting B vector onto each column and dividing by the length of the column, the projected length by the length of the column vector will give us the solution. It is also important, so it will be important if we can transform the basis of the column space to mutually orthogonal basis. So, what will happen when we have some vector like that, say 3 0 0 0 3 0 0 0 4 x y z is equal to 5 6 7. So, I can say that x is equal to, if I project this into 3 0 0, this will be 5 0 0. So, x is equal to 5 by 3, y is equal to 6 by 3, z is equal to 4 by 7 by 4, something like that we can find out. Instead, if we have a columns in a rotated form, so these are not 3 0 0, but for example, if I have column like 3 2 0 and then minus 3 2 0, right, minus 2 3 0, minus 2 3 0 and 0 0 1. There this is not 3 0 0, they are not in diagonal form, but also here the solution can be very well found in that way. You just multiply the project the vector onto the b vector onto each of the column and find out the length and divide by it. There can be the thing, and the idea of having mutually orthogonal column is that one column vector transpose dot product with another column vector, transpose of one column vector multiplied with another column vector will give you a 0 if the indices are not equal. This will be, there will be a further advantage if we can have orthonormal basis. That means the columns are perpendicular to each other and the length of each column vector is 1. So, when we are doing this division, divide this. So, when we are dividing that, divide the projected length by the length of the column. If the columns are, divide the projected length by the length of the column, if the columns are orthonormal, then this length of each column is equal to 1. So, if we only find out the projected length of b vector along each column, that is the solution, that is the coefficient multiplied with each column. So, getting orthonormal column vectors will be of further importance, further use. So, in Rn, these vectors will be called orthogonal q1 q2 q1 if qi transpose qj is equal to 0, if j is not is equal to I. The vector q1 q2 qn are called orthonormal if they are orthogonal along with qi transpose qi, that means length of each vector is equal to 1. So, we can see some of the exercise examples like 4 0 0 0 minus 3 0 3 0 is an orthogonal basis. However, length of the first vector is 4, second 2 or 3. So, they are not orthonormal. In 1 0 0 0 1 0 0 1 0, this is an orthonormal basis. This is 1.867 001 minus minus 0.5 0.86707, they are orthogonal basis as well as they are orthonormal. In an orthonormal basis, each vector must have unit length, because each of these vectors have unit length. So, they form an orthonormal basis. Or orthonormal basis is orthogonal basis, but it is normal, that means each vector has unit length. And this is important in terms of solving equations. We saw that only the length of the projection will give us solution here. A matrix with orthonormal columns is denoted as a Q matrix. Q is general form of a matrix which has orthonormal columns. Now, there can be any number of columns, it can be a rectangular matrix. However, if it is a square matrix with orthonormal column or a Q matrix which is square is called an orthogonal matrix. Remember, this is a terminology, it is not called orthonormal matrix, it is called orthogonal matrix, because it is conventionally it is being said. So, however, for an orthogonal matrix the columns are orthonormal. There can be some example of orthogonal matrix. In all these cases the columns are orthonormal. So, this is basically a we can write a square Q matrix. Q matrix is a matrix with orthonormal columns. If a Q matrix is squared, it is matrix, it is called orthogonal matrix. An identity matrix, for example, 1 0 0 1 is an orthogonal matrix. A permutation matrix like 1 0 0 0 0 0 1 1 0 0 0 0 1 0 1 0 0. This is also an orthogonal matrix. A rotation matrix, for example, cos theta sin theta minus sin theta cos theta, right. So, if I take dot product among these two things, it is cos theta sin theta minus sin theta cos theta 0, and each column has cos square theta plus sin square theta length, which is 1. They are orthogonal matrices. Now, we will look into some important properties of orthogonal matrix. If Q is an orthogonal matrix, Q transpose Q is equal to 1. Sorry, Q transpose Q is not 1, Q transpose Q, I am sorry, is equal to identity matrix. Identity matrix. So, these are each rows of the Q transpose, which is orthogonal row of the orthonormal matrix, column of orthonormal matrix multiplied with the columns of orthonormal matrix. So, this becomes first column of orthonormal matrix and its transpose with the first column of the orthogonal matrix, and this is 1. And for any other value of Q 1 and 2, Q 1 transpose Q 2, this will be 0. So, it becomes 1 0 0 and 0 1 0 0 0 1. So, it becomes an Q transpose Q becomes an identity matrix. And if Q is orthogonal, that is square, so this is for any Q matrix, it not necessarily has to be a square matrix. However, if Q is square, we can say Q inverse is equal to Q transpose. Why? Because for Q, as we have seen, Q transpose Q is equal to I. For square matrix, square Q, Q inverse Q is also identity matrix. So, it gives us that Q inverse is equal to Q. So, for an orthogonal matrix, its transpose is its inverse. So, if we have an orthogonal matrix multiplied with a vector and we have to find out the solution Q x is equal to B, it is x is equal to Q inverse B is x is equal to Q transpose B, and it is trivial to find out the solution in this case. We just make transpose of Q matrix, take it into right hand side, multiply with the B vector, and that will give us solution. So, this is a way of very utility, that inverse is equal to transpose of the Q matrix. Q inverse is equal to Q transpose. Multiplication of a vector with a Q matrix, a matrix which has orthogonal columns, preserves the length of the vector. And we can see that if I have a vector Q multiply with Q vector x multiply with Q Qx and take its L2 norm Qx transpose Qx is equal to x transpose Q transpose Q, and which is the term Q transpose Q is nothing but an identity matrix. So, it is x transpose x is equal to x square. So, if a vector is multiplied with Q, the length will be essentially same. When two vectors are multiplied with Q, their dot product remains same, and the proof is very similar, that I have QA transpose QB is the dot product of A and B, and I think they are vectors. So, I think I should not write this. The proof is like Q A transpose QB. So, I deleted the capital A and writing small a, because for vector we usually use small letters, and A is usually used for matrices which is not column or row vectors, which is m into n order or 2-dimensional arrangement. For 1-dimensional arrangement we use small letters anyway. So, this is A transpose Q transpose Q B. Similarly, like Q is a matrix with Q as Qi as columns. This Q, small q is a column vector, and when we have number of column vectors we get the Q matrix anyway, and this Q transpose Q is identity. So, this is A transpose B. So, dot product between two vector remains same when we multiply the both the vectors with Q, and the angle between the vectors should also then remain same when we multiply them, because dot product is, we have seen, that is shows inequality. Dot product is related between the angle between the vectors. If a vector B is expressed as a combination of orthonormal basis q1 to q2, or we write B is equal to x1 q1 plus x2 q2 up to xn qn. So, there is an orthonormal basis for Rn and B is a vector in Rn. So, you can express B as the combination of this orthonormal basis, some constant coefficient into each of the column vectors, basis vectors, and the combination is vector B. The coefficients can be calculated as take q1 transpose multiply it with B. So, q1 transpose x1 q1, q1 transpose q1, x is a scalar, it will come outside, q1 transpose q1 is equal to 1. q1 transpose x2 q2 is x2 into q1 transpose q2, and as q's are orthonormal, q1 transpose q2 is equal to 0. So, there will be q1 transpose B is x1 q1 transpose q, which is this is 1, this is 0, this is 0. So, this will be x1. So, finally, B can be expressed as B is equal to, so x1 is q1 transpose B, similarly x2 will be q2 transpose B, x3 will be q3 transpose B, and so on. B is equal to q1 transpose B q1 plus q2 transpose B q plus qn transpose B qn. So, coefficients associated with each of the basis vectors is equal to projection of the vector of the main vector on each basis. This is a very important, extremely important way of expressing a function vector. This can be utilized for vectors, like when we write a vector is equal to 3i plus 4j, that means its projection on I along I vector is 3, projection along j vector is 4. Also, in certain cases when we do Bessel function or Fourier functions, Fourier series expressions, when there is an expression with mutually, or there is an expression of continuous function. Continuous functions are vector spaces in R infinity, we have seen that earlier. So, there is something in R infinity, there are infinite orthonormal bases, and we can express any function as combination of this infinite orthonormal basis. If you can remember Fourier series, the coefficient for each term in Fourier series, each sine or cos term in Fourier series is found out by taking the main function and then multiplying it with that cosine function or sine function cos omega x or sin omega x, and then they are doing their integration and normalizing it. So, this is basically projecting the main function along each of the basis vectors and finding it. So, Fourier series, it is important, Fourier and Bessel series, Fourier series, Legendre polynomials, all these series functions are composed of orthogonal basis vectors in R infinity, and we can express any function like that. So, nevertheless, Fourier series is as of now out of purview of this particular syllabus. So, we will move on. So, we will look into normal equation with orthogonal columns. Let us start with rectangular matrix A with equation system A x is equal to f. A has independent columns, therefore, there can be at most one solution. However, f does not lie on the column space, and so a least square solution or a normal equation is to be solved. Now, A, some way we transformed A to Q, we will look into this transformation, and now the equation is q x is equal to b. So, we did some matrix transformation matrix operations on A and got a form A is equal to q. Q is a set of q has orthogonal columns. So, we got the equation q x is equal to b. Q x is equal to b is a rectangular system with no solution for most b. If b does not lie on the column space of A, there is q, there is no solution. The normal equation is q transpose q x tilde is equal to q transpose b. So, normal equation for best x tilde which in which we can now say that q transpose q is equal to I, because q has orthogonal columns. So, the normal equation reduces to x tilde is equal to q transpose b. So, we have basically we have the solution that write it here x 1 x 2 up to x n is equal to q 1 transpose b, q 2 transpose b, so on q n transpose b. So, the solution is in one line if we can express A as q, and then we can see that P is equal to q x tilde, which is the projection of B into the normal into the column space, is basically x q multiplied by x. So, q tilde of B. So, this is q 1 transpose B q 1 plus this is basically B expressed in terms of the q vector q 1 transpose B q 1 up to q n transpose B, and the projection matrix is q transpose. So, again these are interesting to look like how is q transpose, all these things. However, what we can see is that the least square or normal equations becomes very simple to solve if we can express A as q, and that will give us the next drive, that if we can transform A to q, or we can form orthonormal basis of column space from a given set of column vectors. We have a set of column vectors basis of the column space which are not orthogonal. So, we cannot write q x is equal to b and solve it very easily. We have A x tilde is equal to f, and then we have to solve it like the normal equation A transpose A x tilde is equal to A transpose b. We will come into it later that solving normal equation, especially when we use iterative methods, has certain implications. We will come into it later. But q transpose or what we got q x is equal to q transpose b, we do not need to solve it, it is already solved. If we can express A is equal to transform A as q in the normal equation, what we observed in the last slide, for example. So, if instead of solving A transpose A x is equal to A transpose A, if we can solve the normal equation in this form, which is very simple, it is already solved, we do not have to do anything. So, that is our focus in next slide, that it is useful to transform A to q to form an orthonormal basis of column space from a given set of column vectors, and this is called Gram-Schmidt process. So, we have a basis which are not perpendicular to each other in R2, which are not orthogonal basis vectors A and B. What we do? We get an unit vector out of A, because our target is to get orthonormal basis. So, we divide A by its length and get an unit vector q 1, which is an unit vector q 1. We project B onto A, and this projection, as we have seen, q 1 is the unit vector. So, this projection will let us project it into the unit vector. So, the length etcetera preserves. So, P becomes q 1 transpose B q 1, because q 1 is along unit vector along A, projection along B, or projection along A and projection along q 1 will be same, the projection will be same, and the left out part is B minus q 1 transpose B q 1. So, this left out part should be perpendicular to the projected part P or perpendicular to q. So, now we can make another basis using the left out part. So, what we will do? We have found this part, we have found q 1, this is another q 1 is, let us say q 1 is one basis, this is also, this should be independent, B, capital B, which is B minus q 1 transpose B q 1 is independent from q 1, they should also form a basis, and we will normalize it, divide it by its length. So, we will get an orthonormal basis. Before that, sorry, here we got an orthogonal basis in R 2, A and the B vector B minus q 1 transpose B q 1, and then these two, the vector A and this vector A and B, they form an orthogonal basis in R 2, and now we divide both of the vectors by their length. We got q 1 and q 2 who form an orthonormal basis in R 2. So, this is the idea of Gram-Schmidt process. You take two vectors, project one vector onto other, and the subtract part from the main vector and the projected vector will be perpendicular to the projection, use these two and form an orthogonal basis. So, this is very straightforward for two vectors, finding considering a vector, finding its component along one particular vector and perpendicular to that particular vector. But when, so this is what we call Gram-Schmidt process in R 2. We have the vector B, project vector B to A, we have a vector A, and then find out first orthogonal basis by dividing A by its length, which is q 1, then project vector B to vector A and get the subtraction, which is B minus q 1 transpose B q 1, and divide it by its length. So, you get q 1 and q 2, which are orthonormal basis. So, these two q 1 and q 2, they are orthonormal vectors and they give a basis in R 2. Now, if we go to R 3, we have three basis vectors. We do the exact same part for first two basis vectors. The third one is away from the plane. The for two vectors will form a plane. On that plane, we found similarly q 1 and q 2 two basis vectors for that particular plane. For the third one, first from q 1 and q 2 with two vectors as it was done in R 2. Now, for the third one, from C subtract the component which is in the plane in form of A and B. Now, this plane now has an orthonormal basis q 1 and q 2. So, project C along q 1, project C along q 2, subtract it from the C, and you get capital C is C minus q 1 transpose C minus into q 1 minus q 2 transpose C q 2. So, you get capital C, and then the third orthonormal basis q 3 is formed by normalizing C to unit vector C by modulus of C, and then we can, so these three becomes a orthonormal basis vectors. So, then we can continue it for higher dimension. This is the one idea of whole Gram-Schmidt process. Subtract from every vector, every new vector, its component in the directions that are already settled. So, you get first you get two vectors, settle this, like get two orthonormal basis vectors, settle these two vectors. Then you have the third vector, you subtract the component of the third vector which are when you project the third vector onto the two already settled vectors and then subtract the component from there. So, you get another vector which is perpendicular to the first two orthonormal basis. So, this normalize it, get the third orthonormal basis. So, you subtract every new vector from the components that are already settled and then normalize it, divide it by its length. The idea is used over and over again. When there is a fourth vector, we subtract away its components in the direction of q 1, q 2, q 3. So, Gram-Schmidt starts with independent vectors a 1, a 2 up to a n and ends with orthonormal vectors q 1, q 2 up to q n. At each step it subtracts from a vector a j, which is part of the earlier basis, its components in direction q 1 up to q j minus 1, which are already been found out, and there that are already settled as a j is equal to this, and then it divides a j by its length and get the latest orthonormal vector in the set Qj, and so on. It can go for a number of vectors and find out the it can take number of basis vectors and find out the same number of orthonormal basis for any set. So, Gram-Schmidt process can be obtained for m independent vectors in Rn. So, it is not necessary that it has to form a basis. You just have to have few independent vectors and then create mutually orthogonal independent vectors out of that. So, take independent vectors which are inclined to it and then create a set of mutually orthogonal vectors. So, now the question is how we can apply it for the matrix equations. If the number of vectors, independent vectors in the initial set or number of columns of the matrix is all these are independent. So, all these are independent columns. So, the number of columns in this space is equal to the dimension of the real coordinate space, then we have a square matrix and we have a perfect solution. If it is not, we may have a normal equation, we have to find out the best estimate. However, how can we start with a matrix A, normalize its columns, orthonormalize its columns, get a Q form and solve Ax is equal to b? That will be the question which we will address in the next few classes. Thank you.